In this video, I'd like to introduce microscopic entropy, which is maybe a more detailed way of thinking or maybe a more fundamental way of thinking about entropy than what we've done so far. And if you think about what we've done in the course so far, we've calculated changes in entropy that occur due to a process. And if that process is reversible, then we can compute that change in the entropy as, let's say, the integral of how much heat was exchanged in that process divided by T. And in this case, it's up to us to decide how best that we can integrate dq by T. So for example, in the case of something that was isothermal, if it's an ideal gas, that's going to give us some information on how we can treat this dq in the numerator of the integrand, and then we can compute how much entropy was gained or lost, let's say by the system, due to this particular process. Now, what I'd like to do is talk about something that's much more fundamental than this. Instead of talking about what the change in entropy would be between two processes, let's see if we could calculate what the entropy of something is to begin with. And to do this, let's imagine that I build a machine. And what this machine is going to do, let's say this is going to be my machine, right? So we've got this. And let's just say that this is going to spit out a letter. Okay, so we'll say that there are four choices for letters that this can spit out. It can spit out, let's say, A, B, C, or D. And so as we turn this crank, every time the crank goes around, it's going to spit out a letter. And so let's say that the sequence looks something like this. The first letter it spits out is going to go here, and let's say that it was an A, and then we had something like an A, and maybe we got a B, and then, I don't know, a D or something like that, right? So that's what our machine has spit out to us. And so what we would like to do is say, okay, well, if there's a certain number of options that we have for this machine to give us, and if those options occur with a certain probability, what goes into, let's say, predicting what the next letter in a sequence would be? So can I predict maybe what the next letter in this sequence is going to be if I know something about the probability with which those are going to occur? And so as an example, let's specify what those probabilities would be as an example. So the probability, let's say, of A occurring, let's just assume that it's 50%, okay? So we've got a 50% chance of our machine spitting out A. And let's say that there's a 25% chance that it spits out B. So the probability of B occurring is 25%. And let's divide up the probabilities of the last two options and see what those would be. And so the probabilities, let's say, of C occurring would be the same as the probability of D occurring. And let's say that those are both 12.5% each. And so what you can see is that all of these possibilities here add up to a total of 50%. And then these two options here add up to a total of 25%. Now, is that important or not? Well, we'll see in a second, okay? So, okay, those are the probabilities with which these letters are going to occur. And as an aside, you could think about what this means in terms of, let's say, the 26 letters that make up our alphabet in the English language, and the probability with which those would occur, and how those may differ from, let's say, the probabilities that certain letters would occur in Spanish or French or Portuguese, or, you name it, right? They're going to occur with different probabilities, at least in principle, depending on the language that you speak, okay? So that's kind of, let's say, is analogous to what we're doing here. So I'd like to guess what the next letter is. And so let's say I make a prediction, then I've got to check whether or not my prediction is correct. So the way that I would do this is I can ask a series of yes or no questions to see whether or not my guess for the next letter is going to be correct, okay? And so let's see how we would do that. So I'm going to do this. I'm going to ask a series of yes or no questions. And of course, a yes or no question has two possibilities for the answer, right? It can either be yes or it can be no. And so how would I check whether or not my prediction was correct? Well, let's do it this way. Okay, so let's say that we start off and we've got four possibilities, right? We have A, B, C, or D as the possible options that could be spit out by the machine for the next letter, right? So this option right here could be A, B, C, or D, and we'd like to see if whatever I guess, I'm not saying what I guessed, but right, but let's say or we're trying to see whether what I say is going to be the next letter is correct. So how would I do that? Well, I can just pick one of them, and I'm going to choose this in a very particular way. I'm going to ask the question right here, my first question. Is it A? And if you think about that, 50% of the time, the answer to that is going to be yes, right? At least based on these probabilities, the probability that that thing is going to be A is 50%. And so, you know, if the answer to this question is yes, then the letter is A. And if the answer to this question is no, right, I can't say what exactly the letter is, but I know that it has to be either B, C, or D. So what this means is that 50% of the time, I only have to ask one question to see whether or not my prediction for the next letter was correct. And we'll come back to that in a second. And so what would I do if I wanted to guess the rest of them? Well, I do a similar process. I would start to ask yes or no questions, and I can ask them in a very clever way so that I can minimize the number of questions I have to ask. And so the next question I could ask is right here, question number 2, is it B? And now that we've eliminated A as being a possibility, if we look at what's going on here, for the remainder of our letters, right, for B, C, and D, 50% of the time, so 50% of the time, the answer is going to be that it's C or D, and 50% of the time, the answer is going to be B. So it's kind of analogous to what we did in the first step. And so if the answer here is yes, then we know that our letter is B. And if the answer to this question is no, then we know that the only options that are left is that our letter must be C or D. Okay, and again, that's if the answer is no. And so you can see for this series of questions, every time we ask a question, we kind of branch off in two, right? We've got two options. Either the answer to that question was yes or the answer to that question was no. And then if we want to figure out, if it's not A and if it's not B, then clearly the only other option is C or D. And we can ask one more yes or no question, which is it C? Or equivalently, we could ask, is it D? Right? So the third question, we could ask it either way. So is it C or D? We're going to only ask one of those questions, right? So is it C or is it D? And let's just say that we're going to just focus on is it C, right? Just to make this a little cleaner. Okay, so the question we're asking is it C? And if the answer to that is yes, then obviously that letter must be C. And if the answer is no, then we know that that letter was D. And so notice that every time we do this, we're kind of branching off and we're getting a little bit more information about whether or not our guess was correct. And so basically here to determine whether or not the letter was A, we only had to ask one question, right? So this was one step in the tree. One step in our little tree here gave us information about whether it was A or whether it was something else. If it was something else, then we need another step. So we took another step here to narrow it down to see whether or not it was B. And if the answer was no, then we needed to take one more step right here. Right, one step to see if it was C. And so each of these times, we got a little bit of information. Let me make it a little bit more explicit. After one step, what did we figure out? We figured that it was either A or, so we'll use that upside down V, right, as a symbol for or. It was either A or it was B, C, D after that first step. After the second step down our tree, we figured out if it was B or if it was either C or D. And then by this last step, we've narrowed it down completely. We figured out whether it was C or whether it was D. And so that's what we've kind of done in guessing whether or not our prediction for the next letter is correct. We've broken it down into a series of questions, and each of those questions can branch off in one of two directions each time. And so, you can think about it this way too. I needed to ask one question to find out if it was an A. I needed to ask two questions to find out if it was B, and I needed to ask three questions to find out if it was C or D. And so, that's kind of what I'm saying by saying that we've taken these different steps, right? And that's how we've gotten this information. And then if you look at the tree itself, right, I had two options here that I could take, right? I got two different paths I could take. I had two different paths I could take here, and I had two different paths I could take here. And so I had total, after the first one, I had 2 to the 1 possible paths that I could have taken. After the second step, I've got 2 squared paths that I could have taken. And after the third step, I've got 2 cubed or 8 paths that I could have taken. All right, so let's ask maybe a more useful question then, right? That's checking one letter. But in general, like if I wanted to check my guess, right? If I wanted to see if I was correct, then how many questions do I need to ask for every letter that's spit out to see if I was correct, right? So the question I'm trying to answer is, on average, how many questions are needed to check my guess for a letter? And we could just sum that up. I'm going to call it S. You can probably guess why I'm calling it that, right? Well, let's see. A occurs 50% of the time. The probability of A occurring is 50%. So 50% of the time, I only need to ask one question. Okay? But 25% of the time, that letter is going to be B. And so that means that 25% of the time, I'm going to ask 2 questions to figure out what my letter is. And then 12.5% of the time, my letter is going to be C or D, and I'm going to have to ask 3 questions to determine whether or not that's true. Okay? So basically, what this is saying, let's add a little bit of color here. This is saying 50% of the time, I only need to ask one question. So I ask one question, right? 25% of the time, I have 2 questions. And then, this is going to tell me if it's A, this is going to tell me if it's B, and I could come up and I could write similar things here, right? 12.5% of the time, I'm going to have to ask 3 questions, and that will tell me whether it's C or D. And so we could add this up, right? We can add up these numbers, and we would see that on average, for any given letter that this thing spits out, I need to ask on average about 1.75 questions. All right, so that's just how many questions I need to ask on average. And notice for each of these steps, right? For the first one, we had to ask one question. One question is basically equal to the log base 2 of 2, right? And that's, well, we'll just leave it like that, right? 2 questions is equal to the log base 2 of 4. Let's write it 2 squared. And 3 questions can be written as log base 2 of 8, 2 cubed. Okay, so clearly the number of questions that we have to ask to determine whether or not our guess was correct is tied in somehow to the number of different branch points we have, right? The number of different ways we can get to a certain place. And we could also express these things in terms of probabilities, right? So this is the same thing as if I wrote minus log base 2 of 1 over 0.5, right? 1 over 0.5 will give me 2. Well, let's put it a different way. I put 2 in the denominator and I bring the minus sign in so I can put it in the denominator. How about that, right? And so I can also write this as minus log base 2 of 1 over 0.25. And this is this is log base 2 of 1 over 0.125. Okay, so the number of questions that I need to ask to determine whether or not my guess is correct can be tied to the probability with which those letters are going to show up in our sequence. And you could imagine that if I broaden this to 25 letters, each of which occur with a different probability, I could start to maybe model the English language. And hot take here, maybe that can be used to come up with the best guess for your first Wordle entry if you're trying to solve that New York Times puzzle. In fact, Veritasium, the YouTube channel, has a whole video on just how to choose the optimal Wordle guess, given, whatever it is, 5 letters and the probability with which certain letters occur. Okay, kind of interesting. All right, so what do we do here? Well, let's just define this thing, okay? So we can define this thing that I've called S as, let's say, minus, the sum will be a little bit more formal here. We'll say over the possibilities that are in, over the different possibilities that are in the set of outcomes, if you want, of the probability that that thing will occur, and then log base 2 of that probability. And log base 2 is coming from the fact that every time we ask a question, we kind of narrow down, we kind of split our answer in half here. All right. So in general, this was done in 1948 by Claude Shannon. So in general, you could write this, I think he called it H, but you could define H as minus the summation over these different options from all of the possible ones, the probability that that thing will occur, and let's just say log base B of P of X. All right, and again, we chose B equals 2 because every time we ask a yes or no question, there's 2 answers, and so we kind of split off from this. If we set the base to be 2, then the units of the Shannon entropy are bits. Okay? So this goes back to information entropy and information theory and the definition of information. You can see the natural connection between this kind of interpretation and the amount of information you could store in a computer, or maybe the amount of information you could store, period, right? Because you can represent any kind of information as a series of zeros and ones. That's how your computer works. So let's look at something related, okay? So and then we'll come back and kind of tie this together. So what if, instead of having those kind of skewed probabilities, what if the probabilities were all equal, right? So the probability of A was equal to the probability of B occurring, equal to the probability of C occurring, equal to the probability of D occurring, right? And so those all have to be 25%. So what if that was the case? Then if what I've written up here is true, right? If this is related to the average number of questions that I need to ask to check whether or not my guess is true, then I could calculate in this case how much I need to ask, right? How many questions on average I need to ask. And so in general, since they're all the same, I could write that value of S, which I'm going to call the entropy in a second, right? The value of this Shannon entropy would be, again, minus the summation of all of the possible letters that I've got in my set of letters. There's another way of saying that. Probability of that letter occurring multiplied by log base 2 of the probability of that letter occurring. Now, these are all the same, right? So this is actually equal to minus 4 times 0.25 log base 2 of 0.25, which again is the same thing as 4 multiplied by 0.25 log base 2 of, see, we bring the minus sign in, so this becomes 1 over 0.25 log base 2 of 4. And so this becomes, what, 2. 2 bits is the unit. So we go up here, according to our thing up here, right, originally with the skewed probabilities, we had 1.75 bits is what that formula would have given us. And so in this case, we've got 2 bits, we could say, of information in the system. And in the first one, we had 1.75 bits of information. So clearly, when the probabilities are all equal, so the S here, let's call this S of system 2, compared to up here, this is the S of system 1. Clearly then the S of system 2 is greater than the S of system 1. And what we would say in this case is that system 2 has higher entropy. In other words, we need to ask more questions to figure out what the letter is. And so each question we ask is giving us a certain amount of information. So this is also kind of implying we need to ask more questions. Okay. And if we need to ask more questions, then what does that really mean? It means that we know less about our system. We are more ignorant about our system. So we, in general, know less about system 2 than system 1. Okay, and so all these things are kind of equivalent to each other. So for equal probabilities, our entropy is higher. All right. All right, now how are we going to tie this into any kind of information or any kind of concept that's relevant, let's say, to polymer physics? Well, first of all, we can define a couple of different entropies. And so what I just defined here, again, Shannon called it H. I'm just going to call it S to keep our notation kind of consistent here. What we defined here is what we call the Shannon entropy. Okay, so we defined S as minus the summation over the options in our set of options, P of X, log base B of P of X. Okay, so it doesn't have to be log base 2. Log base 2 is a convenient choice for a lot of systems, though. All right. We could get a little bit more specific in this case, and we could introduce a conversion factor, and we could introduce a conversion factor that we call KB, and that's 1.38 times 10 to the minus 23 joules per Kelvin. All this is a proportionality constant, right? It's telling us something about, for every Kelvin, how many joules of energy are associated with it. And in some sense, this is an unlucky choice. Maybe not unlucky, but it's the result of the units that we're using, okay? The result of the SI units that we use. So if we were an alien species and we defined energy and absolute temperature differently, then we would have a different value for this proportionality constant. Or maybe we would choose things where these things are all 1 and that constant would go away like it does in the Shannon entropy. I'm kind of getting into the weeds here. But if we do this, then we could define what we call the Gibbs entropy. And in some sense, it's like the Shannon entropy, but it's got this proportionality constant, KB, and it's also got a different base. And so we could define the entropy as minus KB. Again, the summation over the options that are possible in the set of all options, and I'll make that a little bit more specific in a second, of P of X natural log P of X, right? And remember, natural log is just log base E of something. Okay, so we've got the Gibbs entropy. And we could define also what's called the von Neumann entropy. That's an entropy that's more relevant to quantum mechanics. And so that's not something that's super useful to us right now as polymer physics students or polymer physics instructors or whatever, right? But we could assume that maybe all of the things that can occur with equal probabilities, right? Kind of analogous to system 2. And so from the Gibbs entropy, we could define what we call the Boltzmann entropy. After Ludwig Boltzmann. And, you know, I should say chronologically, the way I presented this is not exactly the way it actually happened, right? But in terms of getting more specific, this is kind of how it goes. We could define the entropy as KB times the natural log of omega, where omega, we call it the number of microstates But basically it's the number of options, right? So it's kind of like the number of options that are possible. So if you think about it, if we go up here, when we were calculating the entropy, the Shannon entropy of system 2, notice we had log of 0.25, and if we bring that minus sign in, right, this gives us 4 times 0.25 times log base 2 of 4. Well, notice we had 4 options here and they all occurred with equal probability, okay? So there's kind of a connection between these probabilities and the number of microstates. So the number of microstates, we'll say, are the possible ways of rearranging our system to get the same result, okay, to get the same macroscopic result. And so at least in terms of things, or of the way that we would specify it for polymer physics, let's just say here that this we will call, again, the number of microstates. And what it's going to be the number of ways we can rearrange the particles in our system to get the same, what we call the macro state. Okay, so the number of ways that we can rearrange this so that we get the same energy, temperature, pressure, et cetera, et cetera, et cetera. Okay, that's what we're going to call the number of microstates. Okay, this expression right here, so Boltzmann's expression for entropy right here, this can be derived more rigorously than what I just did. Okay, so I just kind of gave you the end result. You could get it if you wanted to, right? You could go through and get this from the Shannon entropy. This can be derived a little bit more rigorously, and so if you're interested, there's kind of like an appendix at the end of the video where I'll show you one way to get it. But if you're not interested in how to actually get this expression, then that's okay. We'll just use this result to better understand the polymers. So what about polymers? Well, let's start with this. Let's draw a polymer. Oops. Let's draw a polymer. And so this is what a polymer looks like in my mind. And we've discussed some of the features, right? So a polymer has a certain, say, end-to-end distance, right? And so we can characterize that, let's say, by the mean squared end-to-end distance. It's got a radius of gyration too, right? It's got a certain average distance that all the monomers in the chain are from the center of mass. And so let's say for this polymer, I don't know, let's say that right there is representative of Rg squared. Okay, so what does all this entropy talk have to do with a polymer chain? Well, think of a polymer chain. It's got a certain amount of energy, right? It's got energy tied up in all of the bonds between the monomers. And so there are also, as we'll see later, interactions between the monomers, right? Other than the fact that they're bonded to each other, right? They can interact with each other locally. So there's going to be a certain amount of energy associated with this polymer chain, right? So there's a certain amount of energy. And as we've seen, there's many different ways that this polymer can be rearranged as well with that certain energy. In fact, let's just pause a second. Let's take a look at a video of a polymer chain from my research group's DPD code. And you can really see all the different rearrangements of the monomers that are possible that give rise to a molecule that has the same energy. So here's a DPD simulation of a bottle brush. So this is a little bit more complicated than just the linear polymer I drew on the screen, but you can see that all of these configurations basically have the same energy, and you can see all the possibilities that this polymer chain has, right? All kinds of ways to rearrange the monomers of the side chains and the backbones and get the same result. And so if you were to look at a bunch of these in solution, then you can imagine that every single molecule could have one of these configurations for its monomers, right? And all these different conformations, just because they're all possible. And so if they're all possible, there's nothing that's going to prevent them from happening. So really what we'd like to do is, considering this polymer chain that I'm showing, we'd like to be able to calculate maybe, well, not maybe, but we would like to be able to calculate the number of microstates right, that are possible given a certain macroscopic state. And from that, the goal is that we would like to calculate the entropy of the polymer chain as Kb times the log of omega. And that's really important because if you think about this polymer chain, you know, if I could say one thing about polymers and only one thing for the rest of my life, maybe one thing that I would say is that polymers, at least at some fundamental level or some fundamental level in polymer physics, are giant balls of entropy. So with that being said, thinking about them, right, it really is important to be able to calculate the entropy because the entropy of the polymers or the collection of polymers is going to be very important for predicting a lot of the properties and behaviors that they have. So for example, if we can determine the entropy of a collection of polymers, then we can understand something about the ability of these things to mix together, whether that's with polymer and solvent or polymers and polymers. We can also use the entropy to understand what the conformation of a polymer or set of polymers is. Conformation, I'm meaning the shape of the molecule itself, like is it really stretched out or is it kind of balled up in some kind of random walk? It gives us a way to understand things like the mechanical properties, especially of polymer networks where the chains are cross-linked to each other. So think of things like rubber. And by extension, you know, it allows us to understand things such as the behavior of materials like hydrogels, you know, among many other. So being able to quantify the entropy of a polymer chain or a collection of polymer chains is something that's really important to understand their behaviors. So let's start with trying to figure out what is this thing that I'm referring to as a microstate. So we saw it in kind of an abstract way when we were looking at that example of the machine that spits out letters, right? But what do I mean in the context of some kind of material? So let's imagine, first of all, that we've got a certain macroscopic property. And let's say that the internal energy of my system is equal to 3 units. Okay, so this U is some kind of unit of energy. And stepping back from polymers for a second, let's just think of simple particles. Let's imagine that I've got a collection of, say, 3 particles. So N is equal to 3 particles. And each of these particles can have a different energy. So when I'm looking at my system, right, I'm seeing that the energy of the system, the internal energy of the system is 3 times U, and I've got 3 particles in there. And so the question is, what is the connection between the microstates, the configuration side of the material, and then what I'm observing macroscopically? And so let me show this kind of schematically, right? Let's maybe draw 4 energy levels. And what I'm doing here by drawing these energy levels, okay, so I'm going to put them in a couple of different configurations. I don't mean this necessarily in the quantum mechanical sense, right? Or I don't mean this in terms of electron orbitals or anything like that. But let's just use this as a schematic to see how we can rearrange the particles, the 3 particles that make up my system, to get that macroscopic result. So let's say that I've got, you know, a certain energy here, a certain energy here, a certain energy here, and a certain energy here. And with respect to some kind of origin for my energy, it's kind of arbitrary, but let's just say that this gives me 0 units of energy, 1 unit of energy, 2 units of energy, and 3 units of energy, you know, whatever that means, right? So how can I rearrange these 3 particles given these energy levels such that I get that macroscopic internal energy of 3U? Well, one way that I could do it, right, is I could put all of the particles in that first or second, however you want to think about it, in that epsilon 1 energy level. And then in this case, the internal energy of my system would be 3 times 1U, or 3U. Probably a little bit more detail than I needed there, right? And how many ways can I do this? I can do this exactly one way. Right? I can do it exactly one way by putting all the particles each in that epsilon 1 energy level. But there are other ways that I could do it too, right? So for example, if I want to look at Another way of doing this, let me draw those 4 energy levels again, and their energies correspond to the same thing that I just drew in the example with them all in epsilon 1. And how could I do it here? Well, I could have, let's say, one particle up here, right? And so this corresponds to an energy of 3U. And I could have the other particles down here, and those are both going to contribute, let's say, 0U to the system, right? So that's one way that I could do it. But that's with, let's say, particle 1 in the 0U level, particle 2 in the 3U, and particle 3 in the 0U. But if I'm thinking about the system overall, it doesn't necessarily have to be that way, right? I could move this one up to that energy level. I could move this one down. And so that would be another way of doing it. So this would be plus one way of doing it. And the other way that I could do it is I could move that third particle to the top energy level and move the other one down. So I could move this one up here, you know, keep this one down here, and keep this one down here. And so I'd have plus one way of doing that. Right? And so the end result is that there are 3 ways that I could do that. In other words, there are 3 microstates in that kind of configuration that give rise to that total internal energy of 3U. And let's just do one last example. I'm not going to count all of these out for you. Turns out there's going to be 10 ways to do it. But again, if I draw those same 4 energy levels, then what's another way that I can do it? Again, this is 0U, 1U, 2U, 3U. If I want to put these particles in, one strategy is I could have one particle here contributing 0, one particle here contributing 1, one particle here contributing 2. And so in this case, still the total internal energy is 3 times U by adding that all up. But there's different ways that I can start to rearrange the particles, right? So it could be the case that this particle was there, this particle was here. It could also be the case that this particle was here, and this particle was here, and I could start to count all the different ways that I can jiggle these particles around, right, such that I get the same total internal energy. And if you count them all up, you can think of it this way. If I take the first particle, and I can put it in either that energy level, or that energy level, then for the first particle, I've got 3 ways that I can do that. And then depending on where I put the first particle, I've got 2 choices for the second particle. And with 2 of the 3 particles specified in energy levels, that only leaves 1 option for the third particle, giving me a total of 10 ways. So if I look at this system as a whole, right, I've got these 3 strategies in terms of putting them either all in the same energy level, by putting 2 in the 0th and 1 in the 3rd, or the top energy level, or this approach that I just looked at here where I put them all in different energy levels. And for this, the total number of microstates that I've got here, I've got 3 ways and 10 ways and 1 way. I've got 14 different microstates that yield an internal energy of 3U. And if these are all equally probable, then you can imagine these things are constantly moving between these different energy levels, giving the same energy for the system. It's just the particles themselves are going to have different contributions to that total energy. And so if I wanted to put more of these particles in, it would get even more complicated. So I'll give you a formula for that in a second. But first, let's see what would happen if these particles can move. And so if the particles, let's say 1, are in constant motion, right? Let's say they're constantly changing their energy levels. If 2, all energy levels are equally probable, then what do I expect? Well, the probability that the particles are going to be all in epsilon 1, there's one way to do that, and there's, you know, a bunch of different ways, or let's say there's, 1 way, 3 ways, 10 ways, so there's 14 ways. So the probability that the system will look like something in configuration 1, well, there's one way to do it, and there's 14 total microstates, right? The probability that the particles will be in the second configuration, where I have 2 particles in the lowest energy level and only 1 particle in the top energy level, there's 3 ways to do that out of 14 total microstates. And if I look at the third one, where the particles are all spread out and they're all in their own energy levels, so the things are really spread out, there's 10 ways to do that. And there's 14, again, total microstates. So again, if I was going into a casino and this was the game, and I had to place my bet on where my particles are most likely to be, this is going to be the most likely way that I'm going to see those particles in the system. So they're going to be spread out between the possible energy levels. And more often than not, that's how they're going to be, right? Now, they sometimes will be in this state, sometimes they'll be in this state, but most likely they're going to be in that state. Okay, so I could start to count these things up, and let's say that I move to 100 particles, or I move to 10 million particles. So I'm going to have to count the ways that I can rearrange 10 million particles to get a certain energy. That kind of gets tedious, right? So the way that I can do it is I can start to think of combinations. So let's say there's only 2 states, right? I could write let's just call it omega. Okay, the number of microstates. Let's say that I've got only 2 states possible. So suppose there are only 2 states. Then the number of microstates that I would get for a certain configuration. Ooh, that's a weird way to say that, right? Let me just write this down first, and then I'll explain this. So I can compute the number of microstates. Sorry, I can compute the ways that I can, the number of different ways that I can rearrange particles in a certain configuration. I can compute that. If I only have 2 states, the ways that I can rearrange the particles between those 2 states, I can count those. And I can count them like this. Okay, so in an expression like this, this is n factorial. Capital N is the total number of particles. This is the number of particles in state 1. This is the number of particles in state 2. All right. So let me give you a simple example of how we could calculate this. I want to calculate the number of different possibilities for putting particles between 2 states in a certain way. Let's take the example of a deck of cards. Okay. So a deck of playing cards. Now, in that case, there's 52 cards. So if you're mean like my sister was, a game you like to play with your younger siblings is 52 pickup. And you're like, ooh, what's 52 pickup? And then they take the 52 cards and they throw them on the floor and they're like, yeah, pick them up. Okay? 52 cards. That's how I know there's 52 cards. Now, if I want to play Texas Hold'em poker, the goal is to assemble a hand of 5 cards, 2 that you have, 3 that are on the table. I think, am I remembering that correctly? Regardless, you want 5 cards or whatever, and you want the best hand. And so how many different 5-card hands exist? How many different 5-card hands exist in Texas Hold'em poker? Okay, so we can calculate that. The number of possible hands that we have, there's 52 cards, so this would be 52 factorial. And then what are the 2 states? One state is that the cards are in your hand. The other state is that they're in the deck, right? And so we have 5 factorial to represent the cards in your hand, and 52 minus 5, 47 factorial. Those are the cards that are not in your hand. And this equals whatever it is. Now, before I tell you what it is, I want you to think about how big these numbers are, right? So let's just look at 52 factorial. Let me put it like this. Let's look at 52 factorial, exclamation point, right? I'm trying to stress here, like, let's look at this number. Okay. Let's not get carried away. Anyway, how big is this number? This number, if you calculate it, is about 8 times 10 to the 67. Is that big or small? Well, it's kind of big. It's like 10 to the 67. No, that's ridiculously huge, okay? And this is 52 factorial. Imagine Avogadro's number factorial. My brain cannot process something that large. How big is this? Let me give you some examples of how big this number is, right? So one example, the number of protons in the observable universe is, on the order of, I wrote it down here, 5 times 10 to the 51. So 52 factorial is bigger than the number of protons in the observable universe. Mind blown. Okay. What is the U.S. debt? Ooh, controversial subject. Last I checked, it was $80 trillion. So 80 times 10 to the 12. Oops. USD. So 52 factorial is much, much, much bigger than that. Okay. Let's say that I paint a grain of sand red. Okay, so I paint 1 grain of sand. And I let you put it randomly on any beach, or let's say any sandy surface, beach, desert, whatever. Any sandy surface on the face of the earth, okay? Hide on any sandy surface. If I was to magically just transport anywhere in the world and pick out 1 grain of sand anywhere in the world, the chances of picking the red grain okay, something like 1 in 1.5 times 10 to the 21. That's the chance that I do that. Really small. And 52 factorial is just huge. So we have to talk about how to calculate that. One answer is, oh, I'm going to plug it in ChatGPT. Oh, I'm going to plug it in Wolfram Alpha. Oh, I'm going to plug it in my fancy calculator. Cool. Some of them can do that. Some of them can't. There's a way that we can start to calculate these numbers. That aside, let's go back to the question of how many different poker hands do I have out of a deck of 52 cards. If I put in 52 factorial and I calculate it in my clever way, divide by 5 factorial, divide by 47 factorial, I find that there's about 2.6 million different hands. Okay. Now, why am I showing you these numbers? Because these are pretty small. 52. I'm talking about a collection of 52 particles, right? 52 cards. The materials that we care about, the number of particles is much larger than 52. And so how do we start to calculate this? So in general, what we're going to do is we're going to define the notation just as we define the notation summation of I over xi is equal to x0 plus x1 plus ... plus xn. We're going to define the notation pi, I equals 0 to n, of xi as being x0 times x1 times x2 times xn. Okay, so big pi product notation. Then from this, or just from these notational whatevers, we'll define that the number of microstates associated with a certain, or the number of microstates, let's just say, is going to be the number of particles I have, total, divided by the product, I equals 0 to whatever, let's call it m, of the number of particles in that configuration or in that partition or whatever, factorial, okay? So let's make this real. Let's go back to this example right here where we were putting these particles in different ways, right? And so the number of microstates, okay, so my example where u was equal to 3u and n was equal to 3, then how many ways are there that I can put the particles in the configuration right here, right, where they're all in the same energy level? How many ways can I do that? Well, I've got the number of microstates associated with that arrangement. Maybe that's the word I'm trying to use. The number of microstates associated with that arrangement would be n factorial, so I'd have 3 factorial, divided by, there's 0 particles in energy level 0. There's 3 factorial particles in energy level 1, 0 factorial particles in energy level 3, right? Basically, all of the particles are in that first energy level, right? That's what's shown in the schematic up here. All right, so let's get rid of that. And we're just going to have 3 factorial divided by 3 factorial, and we get 1. Remember, right? 0 factorial is defined to be 1. Okay, how many particles, or sorry, how many microstates are associated with the second arrangement, with the second scheme of putting them in there, right? Where I've got 1 particle in the top energy level and 2 in the bottom one. Well, I can work that out too. So the number of microstates associated with arrangement 2, I still have 3 particles total. Now I've got 2 particles in that first energy level, 0 in the second, 0 in the third, and 1 in the fourth, right? So I've got 3 factorial, so I have 3 times 2 times 1, divided by 2 factorial, 2 times 1, 6 divided by 2. I have 3 ways of doing that, and that's what I counted up here. I counted for arrangement 2. There were 3 ways that I could do that. And then finally, how many are in this third configuration here where I have the particles spread out between these different energy levels? So we'll just do that, right? The way that they are, the number of microstates associated with that arrangement, I've still got 3 factorial particles, but now I have 1 particle in that first energy level, 1 particle in that second one, 1 particle in that third one, 0 particles in that fourth one, so I end up with just 3 factorial. So I've got 3 times 2 times 1, or I have 6 microstates associated with that, which means that I made a mistake, right? It means that up here, I didn't add right. 3 plus 2 plus 1 is not equal to 10. 3 plus 2 plus 1 is equal to 6, right? There's 6 ways, which means that here when I calculated these probabilities, I didn't have 14 in the denominator. Oops. I actually had 10 in the denominator. So 10 total ways, and that means here this numerator was 6. Sorry about that. That's why it's good to just be able to calculate it, right? And not have to go one by one and start to count up all these ways. In fact, there's no way that you could start to count up all these different ways when you have a real number of particles that exist in real materials. But again, if you add 6 plus 3 plus 1, that will give you a total of 10 microstates that are associated with a total internal energy of like 3. Let's do another example really quickly to show you how these numbers start to really scale when you get to bigger and bigger things. So as another example, Remember, the assumption here is that these particles are constantly moving from one arrangement to another. So the arrangement of the particles is constantly changing, but they're all equally probable. And so let's imagine we have a two-sided container. And we've got a total of 100 particles. And let's say that the container looks kind of like this. And on the left side, we've got 100 slots. And on the right side, we have 100 slots. Okay, and so how many different ways can we put our particles into the system so that they have a particular type of arrangement? So what I mean is, how many microstates are associated with all particles on the left? All right, well, let's see. The number of particles, sorry, the number of microstates where they're all on the left, I've got 100 particles. So I've got 100 factorial. I have 100 on the left, and I have 0 on the right, and that gives me one way to do that. For the exact same reason, because multiplication is commutative, I would find that the number of microstates where they are all on the right-hand side is also equal to 1. All right? What about if I had them distributed 50-50? I had 50 on the left and 50 on the right. How many ways are there to do that? So how many microstates are associated with the 50-50 distribution? Right, well, I've still got 100 particles. I've got 50 on the left, and I've got 50 on the right. And if I calculate this, this is going to be really big. This is on the order of, this is about, let's get rid of that. This is about 10 to the 29. Whoa, that's huge. What about if I had 75 on the left and 75 on the right, or vice versa, right? So the number of microstates associated with 75 on the left and 25 on the right. Again, I still have 100 particles. I've got, let's say, 75 on the left, 25 on the right, and this is about 2.5 times 10 to the 23. There's like a third of an Avogadro's number way of doing that. Now imagine this. I'm in a casino, and the way that I win money is I correctly bet what the microstate of the system is going to be in terms of like where the particles are most likely going to be distributed. They're constantly moving. They can take on any value. Each configuration of the particles is equally probable. Where am I going to put my money? Most likely, the particles are going to be distributed between the two sides of the box. It is very, very, very unlikely that they would be all on the left or all on the right. In fact, it's so unlikely that it just doesn't happen. It's not going to happen ever. The particles are always going to be distributed between the two. So, it's a way of saying, or a way of saying that is the entropy associated with the particles being spread out between both sides of the box, right? 50 on the left, 50 on the right, is much, much larger than them all being on the left, right? Because again, entropy is KB log omega. So the highest entropy state is the most likely state that we're going to see. And at equilibrium, the entropy of the system is going to be maximized. So you're going to find your particles distributed like that. Why do I say they're so improbable, right? It's so improbable to have them all on the left or all on the right that it never happens. Well, consider the universe. How many years has it been since the Big Bang? Our best estimates at the moment are 13.8 billion years. Right, so that's what, 13.8 times 10 to the 9 years. How many seconds is that? 13.8 billion years is equal to 4.3 times 10 to the 17 seconds. So let's imagine every second that occurs, you change the configuration of those particles in the system, right? So they start off with certain number on the left, certain number on the right, and then different positions, right? Because you can have one particle here, right? Whatever. So let's say that every 1 second, they've changed their positions completely. The age of the universe is not long enough for them to have explored every possible arrangement of the particles. And so it's just very, very, very unlikely. It's so unlikely that you'll have all the particles move to one side of the system that it's just never going to happen. Similarly, if we had a room full of gas molecules, right? There's a certain temperature associated with this room, so the particles have a certain kinetic energy. And let's say that we're looking at all the possible arrangements of the gas molecules in the room such that we get these macroscopic properties. Now, it could be the case that all the particles are bunched up on one side of the room. But again, that's so very unlikely. It's so improbable because there's so few microstates associated with that it's just never going to happen. And so that's why the gas particles are found to be throughout the room, because it's the most likely, it's most probable that they'll be distributed throughout the room, because there's more ways to distribute them all throughout the room than there are ways to bunch them up on one side of the room. We'll just never see that. Okay, so that's kind of the connection in some sense between entropy and microstates, and it's getting at a more fundamental definition of what entropy is, as opposed to saying that it's disordered or something like that. It's not really that it's disordered, it's that the highest entropy state is corresponding to the state with the most microstates, and that is the one that's most probable, because they're all exploring all the different ones with equal probability, and so at the end of the day, the ones where they're all mixed up tend to be observed. Okay, so that's kind of the introduction to microscopic entropy. What we're going to do next is we're going to use this concept of microscopic entropy to calculate the entropy of an ideal polymer chain and the free energy of an ideal polymer chain. And with these two things together, we can derive what the conformation of an ideal polymer is, so the freely jointed polymer. And so what we're going to find from that, okay, so from entropy of let's say a freely jointed chain, what we're going to find is the expression that the mean squared end-to-end distance can be written as b squared times n, where again, b is the statistical segment length and n is the degree of polymerization. And what we're also going to find, so this is the first thing we'll find, the second thing that we're going to find is that polymers behave like springs. Okay, so they follow Hooke's law. At least in certain conditions, they follow Hooke's law. And so this is going to come from probability. Okay, so we're going to look at what the probability is that a polymer chain is going to be in a certain configuration. And from that, we can get the free energy. And so the fact that polymers behave like springs is going to come from the free energy. Okay, so that's all I really want to say about microscopic entropy right now. Now, if you care, in the next part of the video, there's going to be a little appendix, and we can derive the fact that the entropy is equal to kb times log omega. That's not really essential for this part, and so if you are not interested in that, or if you don't think you have the energy right now to go through that, then that's fine. But for those of you who are interested, feel free to stay on and watch the last little bit on how we get Boltzmann's law.
1 hour later.
How are we going to derive S is equal to kb log omega? Well, to do that first, let's remind ourselves what the Helmholtz energy is. It's Helmholtz free energy, right? It's the Legendre transform of the internal energy. So we take U, and from that we define F is equal to U minus TS, and that gives us the Helmholtz free energy, right? And then in that case, if we wanted the entropy would be minus the partial derivative of the Helmholtz free energy with respect to temperature, holding what? Volume constant. Right? Okay. So let's do this. The first thing is let's think about the fact that we're dealing with really large numbers here, right? So we're dealing with things like n factorial, which are very large. And not only are we doing that, but we're also more specifically looking at the logarithm, the natural logarithm of something that's very large. So that's a little bit more tractable, right? But let's see what that really means, right? So if we've got the logarithm of n factorial, we've got the logarithm of this big product, right? We have the logarithm of n times n minus 1 times n minus 2 times dot, 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 all the way down to 1. And since we have the logarithm of a product, we can separate that into a sum of logarithms. And so this is the same as the logarithm of n plus the logarithm of n minus 1 plus dot, 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 plus the logarithm of 1, which is 0, of course, right? So what we've done is we've shown that we can take the logarithm of n factorial and we can express that equivalently as a sum as, let's say, I is equal to 1 to n of the logarithm of I. All right? And if we're dealing with something that's very large, so let's assume that n is much, much larger than 1, then in that case, we can maybe approximate this by an integral. And so we can approximate, in this case, the logarithm of n factorial as being approximately equal to the integral from 1 to n of the logarithm of x dx if you want. And if we want to do that integral, we can do it by parts. And this comes out to be n logarithm of n minus n plus 1. And actually, we said n was much, much, much larger than 1. So really this thing, we can ignore this. That little 1 at the end is negligible. And so this is just to say that for n very, very large, much larger than 1, the logarithm of n factorial is approximately n log n minus n. We call this Stirling's approximation. All right. So now, how are we going to get a relationship between the number of microstates and the entropy? Well, let's consider the logarithm of omega. Okay, so we said earlier, so this is kind of like preliminary stuff. The main result we got to before was that we can compute the number of microstates as being n factorial divided by the product over all those different configurations that are possible of n sub I factorial. And so why don't we take the natural log of this? Okay, so we'll take the natural log of both sides. So log omega, which I claim is related to entropy, right? That's in the Boltzmann formula, would be logarithm of n factorial divided by product I equals 1 to m of n sub I factorial. Okay, so we've got that. Well, we've got logarithm of n in the numerator. We have that product in the denominator. And actually, what does this mean? Well, we've got the logarithm of two things being divided by each other. So we've got equivalently the logarithm of the numerator minus the logarithm of the denominator. And so this is equal to logarithm n factorial minus logarithm of the product from I equals 1 to m of n sub I factorial. All right. And again, we've got that product of factorials. And so this is going to come out to the first term here being n log n minus n. And then we've got minus the summation as I goes from 1 to m, or 0 if you want, doesn't matter, of n sub I log n sub I minus n sub I. And so that's Stirling's approximation from the second term. Okay, so we've got the sum. Clearly, if we sum up n sub I, so if we sum up this second term, we're going to get n total. And so this is going to simplify completely so that we've got log omega is equal to n log n, and then minus that sum, right? So we're going to get minus the summation as I goes from 1 to m of n sub I log n sub I. Okay, so what was the point of this, right? We did a bunch of math and we've got this expression. Like, what is this telling us? Well, let's break this down in pieces, and then I'm going to explain the next step. And so the next step is we're going to try to find an expression here for n sub I. Okay, so that's the number of particles that are in that state, that configuration, however you want to think about it. So that's where we're headed next. But let's think about what this expression is. My claim, Boltzmann's claim, is that log omega is related to entropy, and at equilibrium, entropy should be maximized. And we've got this term here that's fixed, right? That doesn't change. That just depends on the total number of particles that you have. And so that's not going to really play a role. But we do have this term here, which clearly does change the value of log omega. And so this, if you want, you could say this depends on the configuration. All right. In other words, the question that we're trying to ask is, what is N1, N2, N3, etc.? What are the different distributions of the particles in these different arrangements that will lead to a maximum value of the entropy? So clearly, our task right now is that we've got to somehow figure out an expression for n sub I, and then what we're going to do is once we have that expression for n sub I, we're going to return to this expression and simplify it, and the end result is that we're going to see a connection between the mathematics we work out and what is the definition of the Helmholtz free energy, and then from that we'll be able to pick out a term that is essentially entropy. So that's kind of where we're going, all right? Okay, so let's think about what has to be true for our system, right? So our goal now is what is n sub I, right? Like, how can I figure out how many particles are in each of these little states? So let's think about what has to be true. The first thing that has to be true is we have a fixed number of particles, right? So our first condition is that the summation over I of n sub I, that's going to give us the total number of particles n. And again, just to say it one more time, that is going to be fixed. We're not going to vary the number of particles in this example. Now you could, but we're not going to do it here. So that's the first thing. The other thing is that there's going to be a certain amount of energy that our system has, a certain amount of internal energy, U. And if you think about it, what we're trying to do is we're trying to come up with all of the different microstates, right, that give rise to the same macroscopic property. And that macroscopic property in this case is the internal energy of our system. That internal energy of our system can be written as a summation over I of n sub I times epsilon sub I, where epsilon sub I is the energy associated with that particular configuration, right? That configuration I. And we're going to say that this is going to be a constant, right? Not unreasonable, and so it shouldn't change. So those are really the two conditions. And so if you think about it now, if we start to take the derivatives, I'm going to say that the derivative of log omega with respect, this notation is going to look kind of weird, but bear with me here. With respect to ni, this should be 0 because we're implying that log omega is maximized. Again, at equilibrium. Okay, so that's got to be 0. The derivative of log omega with respect to ni has to be equal to 0. Furthermore, the internal energy shouldn't change, and so the derivative of our internal energy with respect to ni should equal to 0, which means that internal energy, is constant. Okay, so we've got that. And then finally, the derivative of, again, this notation is kind of weird, but the derivative of n with respect to ni is equal to 0, which is telling us that the number of particles is fixed. All right, so those are our three conditions. And again, we're going to use these conditions to figure out what is n sub I. And then we're going to use that result for n sub I to figure out what the entropy of the system should be. Okay, so in other words, this equation, I know I just numbered these. Let's call this condition A, condition B, and condition C. All three of these must simultaneously be true. So let's write down what these different expressions are, right? So d log omega, we can write as minus the summation over I, right? We're just taking the derivative. If you look here, again, this first term is a constant right here. So that's going to go away, and we're just left with everything else. And so we've got the summation minus the summation over I of what? Log of ni dni, and then plus derivative of the first times the second, right, product rule, plus n sub I over n sub I dn I. Okay, so we got that term. So that term should be 0. Du, we can write as the summation over I. The energy of configuration I is not changing, right? So the only thing that's changing is the number of particles, and so this will be epsilon I dni. Okay, so that should be equal to 0. And that should be equal to 0. And finally, dn, which is equal to the summation over I of dni must be equal to 0. So let's combine all of these things together. We've got a little bit of a problem here. So if you look at d log omega, logarithm has no units, so d log omega has no units. du, that's an energy, so that has units of energy. So those units are not compatible with d log omega, so we're going to have to do something about that. And then finally, dn, I mean, this is number of particles, and so it's kind of got units too. So these all have different units. So we're going to combine these things all together, right? They've got to all equal to 0. They've all got summations in front of them. And so our requirement let's say for ni, or to determine ni, each of these terms has to be 0. And so we're going to say then that the summation over I of logarithm of ni, okay, that has no units, plus beta times epsilon I. The beta's there, I just put that in there. It's going to be a conversion factor that's going to get rid of the units of energy. So it's going to have units of 1 over energy. And then plus alpha, which is just another constant, to get rid of the units on dni right here, multiplied by dni must be equal to 0. And so that is the requirement that we're going to enforce to be able to figure out n sub I. Right there. Okay, so now we just have to do it. And let's say a few things first. Alpha is for units purposes. I'm not even going to talk about what it is because we're going to see that it's not going to matter in the end what alpha is. Beta, on the other hand, does matter. So beta, again, has units of 1 over energy. And so we'll use thermal energy, and so beta will be equal to 1 divided by kBT. Okay, and if we do that, then the units of epsilon I will cancel out. And so everything in that expression will have the same units. So that's important. And now let's just write out the first few terms of the summation just to get a feel for what it looks like. Okay, so I'm just going to write out maybe the first 2 or something. And let's just say, let's remind ourselves this summation goes from I equals 1 to m. And again, let's just write it out. Okay, so we've got for the first term, we've got log of n1 plus beta epsilon 1 plus alpha dn1 plus log of n2 plus beta epsilon 2 plus alpha dn2, first two terms, plus dot, dot, dot. Plus, when we get to the mth term, we've got log of n sub m plus beta epsilon m plus alpha dnm, and all of that has to be equal to 0. And now we run into, we don't really run into a problem, but we've got a condition here, right? The condition is, if this is going to be true, this must be true. Let's write this in red. This is so important, right? This must be true for all dni. All right, and so what that means, the only way that this can be true for any arbitrary dni is that this term must be 0. This term must be 0. This term must be 0. In other words, each of those terms in the parentheses must all be 0 in order for this to be true. And so our requirement then to calculate n sub I is that the logarithm in general, right, the logarithm of n sub I plus beta epsilon I plus alpha must be equal to 0. That's kind of messy. For all I. All right? Okay. And so let's do that. We're just going to manipulate this expression a little bit. We're going to see what we get out of it, and we're going to make some definitions from that. And so logarithm of n sub I, remember what we're after is n sub I, is going to be minus beta epsilon I minus alpha. Let's exponentiate both sides. And so on the left-hand side, we're just left with n sub I, which is what we want. That will be equal to e to the minus alpha, e to the minus beta epsilon I. All right. Okay, so now we've got an expression for n sub I. It's not quite in the form that we want yet. And so why don't we sum up n sub I? And so if we were to sum up from I equals 1 to m of n sub I, we would get the summation as I goes from 1 to m of e to the minus alpha, e to the minus beta epsilon I. And if we sum up n sub I, then what we're left with is the total number of particles in the system, right? And so we're left with capital N. And if you notice, e to the minus alpha doesn't depend on I. And so this is to say that n is equal to e to the minus alpha summation I goes from 1 to m of e to the minus beta epsilon I. All right, so now we've got an expression for n. And what we're going to say then is that this summation right here, this thing right here, we're going to define this as something that's very important. This is called in statistical mechanics the partition function. And so this we will define to be capital Z, and this is what we call the partition function. Some people call it the generating function. If you know it in statistical mechanics, you can calculate a boatload of stuff about your system. It's incredibly important. Okay, so now what does this mean? What we're going to do is, now this is telling us that, how do I want to write this? N is equal to e to the minus alpha times the partition function, which tells us that this factor that was out front up here, in this expression right here, we can solve for that factor e to the minus alpha that's out front. And so e to the minus alpha is going to be n divided by the partition function. All right, and now we can substitute that back in up there. Okay, so after all of that work, what we figured out is the distribution, or the partitioning, if you want, of the particles in these different configurations n sub I or these different configurations I, right? And so n sub I is going to be n times e to the minus beta epsilon I divided by z. Okay, so now if you think about what this is, like if you think about what this is telling us, this thing is a probability. It's the probability of somebody being in configuration I, okay? And if you think about it, what that's telling us then is that the number of particles in state I is equal to the total number of particles that we have multiplied by the probability that they would be in state I. And if you look at it, this is kind of similar to, so this is like in, let's say, general chemistry, when you talk about probabilities for reactions to occur and stuff like that. That's kind of like when you say the probability of something occurring is e to the minus, let's say, delta G over RT. There's some energy difference divided by RT. What we have in this expression for n sub I is some energy E sub I times beta, but beta is 1 over KT. And so these expressions really look quite similar to each other. So if you wanted to, we're not going to use this, but if you wanted to, you could say n sub I is equal to the total number of particles that you've got multiplied by the probability that they would be in state I. Okay, but we're not going to use that. This expression right here, this thing, is what we're going to use. This is what we were after. Okay. So what, right? What was the point of doing all that? Well, let's go back, okay? So now what have we accomplished in doing this? Now we know n sub I, right? If we knew the energies of each configuration I, then we could calculate n sub I. And we did this with the assumption that, or with the requirement that the total number of particles isn't changing, that the internal energy of the system is fixed, and that log omega should be maximized, all right? And so that's kind of where we are right now. And so the next step that we have is we've got an expression for log omega. So log omega is equal to n log n minus the summation, I goes from 1 to m, of n sub I log of n sub I. So we're just going to have to put in our expression for n sub I and simplify this a little bit and see where we end up with it. All right, so that just leaves our last task. So let's start with this expression, and let's put in our expression for n sub I into the expression that I've got right here, and let's see where this leads us. So this means log omega is equal to n log n minus the summation over I. I'm going to start being a little sloppy with my notation right now. If we put in n sub I, we've got n e to the minus beta epsilon I divided by the partition function. And that will be multiplied, of course, by the logarithm of n sub I, which is n e to the minus beta epsilon I divided by z. Okay? We can split this out, right? We've got the logarithm of a bunch of things multiplied and divided to each other, and we've got some constants. The partition function is a constant. The total number of particles is a constant. So this gives us n log n minus the number of particles divided by the partition function, summation over I, and that gives us, let's see here, e to the minus beta epsilon I, and then we can split up the logarithm, and so this gives us logarithm of the number of particles minus the logarithm of e to the minus beta I, so this gives us beta epsilon I. And then we've got the partition function in the denominator, so that gives us minus the logarithm of the partition function. Okay, so all I'm going to do in these next couple steps is just simplify this a little bit. This gives us what? N log n minus, we can multiply each of these terms through, and so we've got what? Log n and log z are constants, so we've got minus n over z log n minus log z, and then we've got summation over I of e to the minus beta epsilon I. So if you're keeping track here, what terms did we simplify? That's, let's see here. We took out this term. Of course, they're multiplied by this term. So we've got to handle the minus beta epsilon I term now. All right, and so in addition to that, we've got plus beta n divided by the partition function, summation over I of epsilon, let's say epsilon I e to the minus beta epsilon I. Ran out of space. Okay. A lot of this stuff is going to simplify, believe it or not. Okay, so what we're going to be left with is, let's see, n logarithm of the partition function. That's coming from right there. That term, let's see here. What am I missing? This term here is just the partition function. And so that means that that term canceled out with this one. Okay, so we've got n log z. And then we've got plus beta n over z. And then that's summation, right? Epsilon sub I e to the minus beta epsilon sub I. And all I'm going to do is I'm going to take these things inside like this. And so I'm going to be left with, let's see here. Let's be very careful. N, again, this is log omega, is n log z. And then, let's see, plus beta summation over I of epsilon sub I n e to the minus beta epsilon sub I over z. And would you look at that? What is that thing that I just wrote? What is this right here? That's nothing but n sub I. Okay, so this is going to simplify a little bit, and we've got n log of z plus beta summation over I epsilon I n sub I. Oh my God, but what is that, right? That's the internal energy. Epsilon I n sub I added up over all I is just the internal energy. And so this gives us n log of z plus beta times the internal energy of the system. And again, that's equal to log omega. So why don't we divide through by beta? Okay, remember, just as an aside, beta we defined as 1 over the thermal energy, kBT. So let's divide through that by that. And so we get out front log of omega divided by beta is equal to n log z divided by beta plus u. And for reasons that may not be clear right now, I'm going to rearrange this in a very particular way. And so I'm going to rewrite this as, let's see, n kBT log of z is equal to u minus kBT log omega. Oh my God, we're getting somewhere. You may not think so, but we are. Okay, we've got that expression. And now what I'm going to tell you, or what I'm going to ask you to do first of all, is compare this. Okay, so compare to the definition of the Helmholtz free energy, where F is equal to U minus TS. All right? And so I'm going to claim, and if you take a course in statistical mechanics, you can, you will derive this, you will go through the reasoning, but at equilibrium, the Helmholtz free energy is equal to N kBT log of the partition function. And so what I've just shown is that the Helmholtz free energy is equal to the internal energy minus kBT times log of omega. And we think back to our Maxwell relations, and what is the entropy? The entropy is defined as minus the partial derivative of the Helmholtz free energy with respect to T, keeping volume constant. And so I would tell you then that from this expression, it must be true that the entropy is equal to minus KB log omega, or the entropy is equal to KB log omega. And again, that's the Boltzmann entropy. Okay, so with just a really simple argument and just a little bit of mathematics, we were able to come up with Boltzmann's original expression for entropy. And so as long as we can count somehow the number of microstates, we can calculate the entropy. And what we're going to do in the next couple classes is we're going to count the number of microstates for a polymer chain, and we'll use that to get the free energy. And then from that free energy, we can get all kinds of things. We can get the behavior of polymers under, let's say, tensile extension. We can get information about the average conformation of polymers. We can get all sorts of things from this. And so keep this in mind as we start to count the number of microstates and what the connection is between the number of microstates, the entropy, and the free energy. I'll see you next time.